Hi, everyone. Welcome. We have Federico Lucifredi to talk about. There's plenty of room at the bottom. Very exciting. Give him a round of applause.
Thank you. So as a little bit of introduction, I had the privilege of spending my entire career in free and open source software, with rare exception for academia. I am the product management director for Ceph at Red Hat. Previously, I was the Ubuntu server PM at Canonical. And if you go back the decade, I was the dreaded systems management czar at SUSE. The talk has nothing to do with my day job. Well, I guess it is if you consider that it's storage in the end. But since I was an embedded engineer, I guess that this is my definition of fun. So, obligatory disclaimer is that we will most likely break some hardware while playing this way. And it will come out of your pocket. No liability if you follow our instructions and stub your toe or bring about the end of the universe. Or break your device, which is far more likely. So you have been warned. Let's get going. We have 60 slides in the demo and about 45 minutes, so we have to run a little bit. The idea. There is a processor in an SD card. Hackaday featured somebody's blog. Pretty much went viral, word of web process, you could call it. Virally blooming once Linux was noticed on the device. And Hackaday made it famous. Lots of blogs, SD card sized, almost a Raspberry Pi. Can we repurpose the device? So on the word of web process that I was describing, blooming once Linux noticed on the device. So I noticed that this was going on, and I wanted a project for Christmas. That was about 4 years ago. So it has taken me for a little bit of a ride. Let me repeat that as there is always someone that has no idea what I'm talking about. Here's the concept. A Wi-Fi-enabled SD card. It's meant to automatically download your pictures from a camera. Several models exist. We are after the embedded system in the SD card. The CPU of the card itself. We're not running Linux from an SD card. We're running Linux on the CPU of the SD card. It's like the Intel Edison that they originally promised us, except that this time it's for real. There are copious amounts of Google Translate we used in the making of this talk. Really international effort, I would say. I saw blogs in French, Japanese, German, Korean, of course, English. And obviously, copious use of Google Translate results in ensuing hilarity. We explored the limits of machine translation, but usually it's clear enough to understand what's going on in there. So the card that I'm looking at specifically is the Transcend Wi-Fi SD line. Comes in size from 8 gigs to 32 gigs. I prefer them as they are more open, even without hacking. There are no attempts at platform strategies by adding any middling cloud services that we do not want. No stepping stone service that may make things easier to set up, and doesn't. And adds another potential place for your pictures to be in. The software on the Transcend card is simple and not perfect, but that's an asset in this case. We will see why. So, where do we get these cards? You can go to Amazon. You could also try eBay. And they're going to be between $40 and $60, depending on capacity, about the price of a Raspberry Pi and up. There are others, like the PQI Air card, that are functionally the same. The PQI Air card is interesting because it is actually an adapter card. You can put any storage you want in microSD format in there, and the adapter actually has the embedded logic, not the card itself. Toshiba makes another one, and there is also the Flu card. And you can carry binaries between them. As a matter of fact, when you log into the system, you may notice there is a command buzz in there. But there are no piezoelectric transducers on the system. So what is that for? But if you look at another one of the cards, that has a piezo. So you can learn things on one card and they are applicable to another. These are all really coming from the same original ODM design that multiple manufacturers purchased. But we're getting derailed here. Let's keep going. When the postman arrives, this is what you get. We're doing the virtual unboxing here since this is way too big to do it live. Inside the package, let's unbox one. A card, an adapter, the inevitable legal disclaimer. There is no legal track in this conference, otherwise I would blame them. And a microscopic bit of manual, which is actually not bad. The adapter is there because you can write to the card directly by mounting it on your Mac, for example, or over the radio. And when you have a file system mounted two places and you are writing from two places, bad things happen. The adapter signals to the card to disable the radio, so prevent simultaneous writes from air and local mount. Of course, that is exactly what we want to do, but we think before we do it. We only want to use the radio, so we will assemble it so that it's not switched off, and we'll be careful about our local mounts. So just what is in there? This is an SDHC class 10 device. 16 gigs in the one that I'm using here. Half and double the size exist. This is a full-size SD card. Picture this model TS16GW SDHC10. You have the slides at the end, so you have all the serial numbers. You don't have to take notes. And you can search for the models, but it's fairly easy to find them even without the part number. So, physically breaking into the device voids the warranty. I bet you didn't see that coming. So X-Acto knifing our way to success. We slice the card in two and find 4 large chips. Interesting. The parts on the left are just a case. Nothing too strange there. Maybe it can be helpful if you're going to dissect one yourself. Incidentally, do you see the yellow tab at the center? That is the write protect switch cards have. Interesting technical detail. There is nothing on the device reading the state of that toggle. The reason for this is that SD cards work the way floppy drives do. If you still remember floppy drives. In floppy drives, write protect is implemented on the device. If the drive sends a write, the card will take it, just like the floppy would. It's up to the drive to implement write protect, not to the card. So the drive will not send a write unless the toggle is in the right place. So overview of the components. From the top left, a trace antenna. Definitely not a 3 dB antenna. And not 100 milliwatts of broadcasting power, as the whole card consumes less than that. So Wi-Fi range will not be per the specs maximum. But that is OK because we're still beating the pants off of Bluetooth. There is no antenna connector. You could try your hand at adding one, or though it doesn't seem very easy. Maybe you're a master solder. But assume that if you don't add an antenna, you're not going to get full Wi-Fi range. And I'm OK with that. Then we have the Wi-Fi radio chip on the top left. The SoC with the ARM CPU that we're going after right underneath it. 16 gigs of flash in the big chip. And the flash controller is the last thing on the right. And up top, you can see the notch where the read-write tab exists. No actual sensing for it of any kind. It's just making space for it. Flip side. Besides the standard SD leads, some of the smaller pads are TX and RX for a 3.3 volt 38400 baud serial. Annoyingly, really annoyingly, they are not labeled. They labeled resistors we don't give a whit about. So I don't know about that, but on the PQI air card, TX and RX pads are properly labeled, so that team gets bonus points for that. If you do wire the serial, you get access to a well-configured U-boot console. If you're not an embedded engineer, U-boot is the bootloader of choice for Linux on embedded devices. It's a very handy tool to have. Grub can do quite a few things today. That is nothing compared to what U-boot can do. It's like having your own operating system, basically. So it is very handy to have access to that, especially because, as you will soon see, the Linux system that comes with the card is severely crippled. So it can be quite convenient. Incidentally, I've been collecting all of these details for a survey article that has been queued now for several years behind a book. I just shipped the book, so the survey article will come out. So if you're waiting until next month or so, you'll get all of these details pretty printed in nice format. Alternatively, if you go and hack, I would like you to report what you do so I can add you to the survey article. So choose your path, lazy or hacker, just act accordingly. What is in there in the 4 chips? CPU, Wi-Fi module, flash controller, and storage. The SoC's 32 megabytes of RAM is the weakest spot on the board. Very suitable for embedded use. Fear not for those of you who are used to gigabytes of RAM. Besides, you have lots of storage, and you could expand these 32 megs with swap, if the kernel was built with swap support. In the SoC, the 8 megabytes of NOR flash are used for the system, and that is why the system is so stripped. It has to fit in these 8 megs of NOR flash that it starts from. And it includes a stripped-down kernel, intra-MFS, and very interesting compromises were made there. We'll see the details. Of course, there is a massive amount of storage. You could boot with a small system, loop mount a larger image, and root into it. If you had loop mount in the kernel. I see a pattern here. But we can add it. Dmitry Greenberg documented how to rebuild this kernel, and so we have the instructions on how to do it. The CPU is 200 megahertz. Some reports indicate 400 megahertz. It's a typo. It's because CPU has 400 BogoMips. They're getting mixed up. They are wrong. It's 200 megahertz. It's an ARM926EJ-S, an ARM9 processor. That is not a Cortex A9. It's an ARM9, much older thing. A low-cost CPU. The architecture was ARM926EJ. More than 5 billion of these were made, with a B. It is a really popular low-cost processor, and it's been in production for 15 years at least. It has interesting extensions for Java, which is the J in that acronym soup I just gave you. But the Jazelle runtime requires a license with ARM, and it was not included with the system. And besides, who wants to do Java these days? The core is interesting. The extensions, E stands for DSP enhancements, because this was used to make feature phones once upon a time. Java for Jazelle. The Java extension makes bytecodes usable. There is an instruction, BJX branch to Java, switches the chip into Jazelle state. The JVM actually handles the errors and the traps, but the processor runs Java instructions. It's actually super cool if you are into Java. Between 134 and 149, I'm not sure why the variance, of the 203 bytecodes in the spec are implemented. If we go back to the Raspberry Pi, the original RPi is a Broadcom BCM2835. 2835, yes. That is an ARM11. There is an ARM11 76J something, but it's not too far off from an ARM9. In fact, it's closer to that than it is to a Cortex. So this is a close cousin of the original Raspberry Pi. So the idea is that instead of the chip on the Pi, you would use the chip on this card. Different trade-offs. You get built-in radio, lose all the interfaces that the Pi has. Price stays about the same. The radio is a Fortune chip, AFN something something. It's a Wi-Fi controller. It contains an Atheros AR6003, which is the smallest, or at the time it was marketed as the smallest Wi-Fi chip you could buy. The smallest Wi-Fi core you could buy, because these things get integrated in bigger chips. The bit we care about here is that it does Wi-Fi B, G, and N. It doesn't do Bluetooth. And that it does do it with very low power draw. It does about 1 megabyte per second of transfer rate. So don't think you're going to saturate anything with this, but it's respectable. Come on, we're talking about an SD card running on fumes here. So do not plan to saturate any link, but you can get 1 megabyte per second. Incidentally, if you feel like going turtles all the way down, there is a CPU to control the baseband radio, an Extensa MIPS core inside this chip. It has 256 Ks of ROM and 256 Ks of RAM, I think. I didn't get into this one. Could be your next project, maybe. The storage is 16 gigs of NAND flash, nothing too interesting, but we certainly are not going to be wanting for storage. Definitely not the problem this system has. The flash controller is a Silicon Motion 2683. Nothing of interest here, except that this is good to argue licensing over. There was a little bit of annoyance in the community because when Linux was found here, people went, where are the kernel modules? So some angry emails were written, some back and forth, and the company published the modules. So nothing to get angry about. This was resolved, and it's no longer an issue. But the module for the controller is not public, because kind of like you're familiar with the discussions about video chips. Flash controller drivers have some kind of secret sauce that the hardware vendors want to keep to themselves. So the vendor of the design doesn't even have access to that. In practice, we don't care about that module. So unless there is someone here from the conservancy, we can write that problem off. There must be some AP restriction. We don't even know what it is. We have the other modules, which lets us build a new kernel if we want. We can just put the driver in there for the proprietary part, as long as we're using the same kernel version. So we're OK. Power. This clocks between 0.9 and 1.1 watts, idle in my office, with the radio on. It peaks at 1.5 watts when the wireless clients connect. This is with a 110 volt power supply, of course, an Apple switched power supply, efficient, but still. We could try to see if the conversion is removed, what happens. Presumably, we would consume more power if we peg the CPU while writing to flash and doing other crazy things. I didn't do that. This is just radio on with clients connected. OK. Interestingly, I also checked what I just said to see if I could get better efficiency with USB power. And we can hardly see a difference. 220 milliamps is about 1.1 watts at 5 volts. So pretty much what we measured at 120. So it closely matches the other one. And it turns out that Apple knows how to design switched power supplies. Good for them. Good job. So let's start looking at the software side. I'm going to walk you through what you do to make this work first, so then you understand what I'm doing when I break in. And it doesn't sound like I'm just talking, but you can actually follow the process. So how does this all work? First, you set up the app on your phone. Then it gives you access to basic setup and core functionality, setting up network mode, names, password. Shoot and view here, the second option, means putting the phone in a monitor mode of sorts, where you take pictures with the camera and they appear on your phone. So you can use the phone as a monitor. There is this automatic download mode, and this will be important later. It also offers you to upgrade the firmware. Usually this is a concern in hacking talks because the precious security hold used for rooting will maybe disappear. That is not the case this time. It does not matter what version of the firmware you have, you're going to get around it. So don't worry about it. The latest version is as open as the first. It is good and bad, I guess. I say it is good because it lets us hack the card. The security issues we bring about are not about the hacking of the BSP, but we'll get into that in a second. By default, the system wants to be its own access point. Great, very convenient for development, but not so for photo download. Think of it. Do you want to switch APs on your handheld device every time you want to sync pictures? The seamless Internet AP client mode is a great strength of this card for ease of use, compared to others that make it needlessly more complex by putting their service in the middle. Here you just choose the mode you want and you get it. No need to reach to mysterious endpoints in the internet. So when it is up, it shows here from another machine in the same room. Your SD card has now become its own access point. Okay, what next? Well, now you can connect to it, just like you would anywhere else. And now you can ping it, just like any other host. So let's look at how it works before we break into it. Think about it. The app needs to find where the heck the card is. It is out there on the access point, but at what IP address? The card broadcasts on UDP 55777. I'm here, I'm here, I'm here. Other cards are even more aggressive. There is one of the models that I mentioned that belongs on the Hall of Shame. It ARPs the entire /24 subnet and finds out where every node is, then sends HTTP requests to every live node and continues until it gets an answer. Then maybe it stops. Most of the time it stops. Don't worry, we can fix this. It's just funny. The tools are only needed for initial IP discovery and password setup. If you do not want to use these tools, the card comes with a convenient default user admin with password 1234567 But that's not the part that will make you laugh. We PORTSCAN the card to see what's going on in there. Here we see telnet, because I already cracked this one. HTTP server. The pictures are published there. The app just HTTP gets them from that web server. Services are offered as CGI scripts in another path of the web server. That's how the app commands the card to do things. The additional port 5566 broadcasts new entries in shoot and view mode. If you're connected there, you'll get a new URL message for every picture. One line saying new URL, new URL. So the app just parses that path. That's how shoot and view works. Very simple architecture, not bad. A few quirks. It downloads pictures twice. Doesn't generate thumbnails. So it downloads the picture once as a thumbnail and then downloads it again to display it to you. It also assumes you are not downloading multiple pictures at once, which are not. So simplicity prevails, no complaints. You can browse the card's HTTP server directly. It's a BOA web server. Exposes directory listings. In theory, it should show you only the directories providing data, and simple CGI bin scripts to set configuration. These are in Perl. The app simply downloads the files and calls CGI scripts, and these scripts are the way in, because we can crack the scripts. That's how the card was broken into. So, all starts with Pablo, who thinks there must be a CPU in these Wi-Fi-enabled cards. Turns out he's right. Pablo went out and started poking at the software, looking for security holes, finds several the size of a small barn, found // backpaths breaking out of allowed area, extracts files, exploits Perl hole, and in it goes. And I went in that way myself the first time, but there is a better way. A file called autorun.sh. I think you know where this is going. Write a file to the SD card named autorun.sh. The system will read it and execute it with root privilege at boot. So all I have to do is just go, telnet please. And telnet arrives. So much nicer. Now, the security freaks among you will be horrified, but in terms of actually working with the card, this is fantastic. It makes it so nice. There is another part of this that is humorously named. I know what you're thinking, but that's not it. It stands for firmware update. It's a clever mechanism. You supply autorun_fush and 3 files. In it are the kernel program bin. The system starts program bin. Turns out this is a copy of the card's U-boot with a default script. Script loads the new system onto the old and then reboots. Nice way to prevent bricking. It also resets all configuration to defaults, which may be handy if you did something wrong. It is a nice way to revert bricking and also gives you a way back to the defaults. You can fix software screw-ups. You cannot fix the hardware screw-ups, but still, this is nice. So it's time to try and do this live. We'll skip the unboxing in the interest of time, since we already saw the pictures. We'll just set one up. So I had to find a USB adapter that would not turn off the SD card radio. And so I conveniently went to my local computer store, bought every single adapter in existence, and after a few tests, I returned 9 out of 10. And I found this one that actually does exactly what we need. And if the demo gods are on our side, we should be able to connect. Unfortunately, I cannot show you the Mac menu on that point. I don't think it lets me. Oh, it does. All right. Let's see if it comes up. So then, we have an IP address. Let's see, I typed this recently, so let's do that. And in we are. So, this boots really fast, which is why we don't see anything. If we were on the serial port, again, same thing, we would just get the connection. It would beat our ability to connect faster than it boots. The boot is basically instantaneous. Now I do my, oh, this is nice. Usually I have to type this turned backwards, so. Let's see if we have tab completion. We do, yay. So this pretty much reflects what we discussed. Kernel 2632, this is one of the most popular kernels ever. This shipped in RHEL 6, SUSE Linux Enterprise 11 SP1, and I think Ubuntu Server 10.04 also, don't quote me on that. It was one of the most popular kernel ever is because the kernel community had this little conspiracy, let's ship the same kernel so we can share maintenance effort. Let's see. SD. Now, this is the VFAT partition. This is the 16 gigs. And we can put all sort of stuff in there. You can see that I mounted it on a Nikon camera. You can see that I have a proper version of BusyBox that is not crippled like the one that's in the system. But I don't have the time to show you the alternate BusyBox. I'm just going to show you the system as is rather than the system the way we want to make it. But we can execute that BusyBox, and suddenly we'll have a full BusyBox environment. Now, this is the partition that we don't want to corrupt. If you have this mounted on a computer and over the radio, this is the place where the double writing happens. So you want files here, and then you want to loop mount those files. So you agree with other agents talking to this file system that that file will be left alone. That it could be one reasonable way to do it. Then, once you have, oh, wrong keyboard. Once you have a working BusyBox, you can use the NTP module so that it's not 2012 anymore. And then that gives you the ability to do SSH because your certificates are not coming from the future anymore. So you can make it work just by adding BusyBox this way, or rather make it work more nicely. But you can also do more. So these are the partitions that you see. The JFFS2 is the 8 gig NOR, the 8 meg NOR partition that the system comes from. It used to be a very popular file system for embedded work. I don't know if it is anymore since now I'm a manager, so I don't do such stuff. But in the last decade, we would always do JFFS2 for embedded systems. So apparently the trend continues. The other stuff is irrelevant. What else do we have? We have, why am I not sad that I don't have Java? Because I have Perl. 5.14, that's actually not bad. Not too old. Then we can look at what's running here. So we have the UDP SVD process, which is the one that spams the subnet, as I described before. There are two of them. Telnet, we started it, so we're guilty about that one. BOA is the web server serving everything out and exposing the CGI scripts. There is actually a DNS, a dynamic DNS announcement. And there is DHCP because we have to serve IP addresses when we are in access point mode. What else is there? The bodyguard process that you see in there is the one that turns off the radio when you plug it into an SD drive. What else? Let's skip the message. That's too messy. Proc CPU. Nothing too surprising here. It looks like I got the CPU architecture right, which is not hard because it's such a common chip. And it is 400 BogoMips, so there you go. Let's see, what do we have? The one that makes me sad. So we want loop, and we want swap. That's what's missing here. And gives you an idea of how strapped for space they were. How often do you see swap compiled out of a kernel? But we can fix that. And then finally, we can list the network interfaces of your SD card, even though it seems like a completely wrong thing to do. There is nothing there, but it's kind of cool. All right, let's go back. We're running a little bit behind. So, actually, the presentation lost the clock, so let's see, 7 minutes. Actually, no, 12 minutes. Perfect. So, as I said before, the system mounts the flash partition under mount SD. So if anything that runs on the system writes to mount SD and other processes write to mount SD, mounting it elsewhere, bad. So don't do that. It's very easy to fix. You can just reformat the file system. But you don't want to do it when your actual application is running there. If you do it during development, sure, no problem. Just rebuild the file system. So what do we have to play with? I kind of hinted it. Kernel module, kernel, those 3 modules are in there. So if you rebuild the kernel, you need to put those modules back in. BusyBox with pretty much all the plugins missing except Telnet, FTP, and DHCP. We can fix that very easily, much more easily than the kernel. So what's the solution for the kernel? The kernel is extremely thin, but it boots, and that's all that it needs to do. Due to the need to fit in the 8 megabyte NOR flash in the SoC, but once we're there, we could loop mount an image from the VFAT partition, root into it, and have a much bigger system. We just need to have loop mount to do this. And we want to also add swap so that we can be a little bit more free about the fact that we only have 32 megs of RAM. We need a new kernel, and a hacker called Robert figured out how to unpack the install files, and then Dimitri Greenberg rebuilt the entire thing, looking at the K-sims, since this kernel doesn't have symbols exposed in proc, so he had to do it a slightly more painful way. So now this work has been done, we can create the live partition out of a single file, loop mount, root into it. Somebody took this to the extreme. So what they did is download an Ubuntu 9 point something image, the last version of Ubuntu that is compatible with this architecture. Downloaded it, put it in the SD card, loop mounted, rooted, forwarded X, started Firefox. Then complained it was slow. It's not too interesting to run Ubuntu from 10 years ago, but it's kind of cool that it could go that far. As I said, where there is Perl, there is everything. This is ARM. So you can cross-compile, you can build on the system, you can use iPackage. You can bring your own language. But if you want to be lazy like any good developer, this is a perfectly viable option. Possibly you will not be able to read what you wrote, but that's OK. The Perl is also relatively recent, 5.14. The big question for embedded devices is, how do you find them? Where is my device? And we need to make it safe for the internets. You cannot behave like I described earlier, ARPing an entire /24. Maybe you can, but you would have to be Facebook. Most responsible people don't do stuff like that. So you cannot use this device if you cannot tell what IP it is at. There are 3 approaches that are common to work with this problem. One is common known configuration. Always be at the same address. This is what I just did. When the card is in AP mode, it is always at the same address, 11.254. So I know where it is. I don't need to find it. Then there is what the card does natively, broadcast, when it is in client mode. It advertises where it is. Besides the horror I described earlier, there are proper advertisement protocols like multicast DNS. MDNS is a perfectly fine way to discover things when you're on a local network. The third one is to announce, which is the device itself, once it has a valid network connection, sends out an announcement. My favorite here is to send out an XMPP announcement. But you can use any protocol you want, and you know this is a unicast announcement to a known endpoint in the internet. It's not a broadcast on the local network. I'm not going to go through all of these. There is an article I wrote for Linux Journal eons ago. Just search for my name, Linux Journal. There are scripts implementing all of these strategies already worked out in Perl that work on this architecture. So just go and grab the scripts. You can also do it right. So if you're a sucker for standards, like some people are, rightly so, in this case, the right standard is DNS update, RFC to 136, which I suffered implementing a while ago. So you have a fixed DNS name that this device always has. When it comes online, it goes to the interwebs and updates the DNS record for itself so that it is known where it is. This is also implemented in my Linux Journal article. It's about 15 lines of Perl. So Perl may be hard to read, but it's very expressive. So let's go back to the security aspect. We were joking about the fact that it was easy to break in. But realistically, this is physical access. We have the card, and we can do things to it. There's no way they could keep us out. We can also do it over the Wi-Fi, which is a little bit more annoying. Fine. That hardly matters. What matters from a security point of view is that this brings the lost USB key attack to a new level. Typical scenario, if you read, if you are in InfoSec or if you read Tom Clancy novels, is that if you want to penetrate somebody's network, you lose a USB key in their parking lot. And then somebody wisely finds it and plugs it where they shouldn't. Some malware gets loaded and whatnot. Now, if you're on a military base, they probably shoot on sight when they see a USB stick laying on the ground. But in most corporate environments, people are still foolish enough that they will do this. And this makes it just worse, because now not only you have installed some malware on some machine that's on the inside network, you also have a radio. So somebody could broadcast some of the data out. Now, the countermeasures to this are no way different from the ones that you would use for rogue access points. So rogue access points, usually you have jamming devices, or you have access points that send clever knacks to any attempt to create a connection from an unapproved access point. Or security for USB keys, which usually involves pouring glue in every USB port that people shouldn't be putting things in. And this doesn't change anything. You can pour glue just as well in the SD slot. Nothing here is new. And these cards are not super secure, but remember, your security posture needs to be commensurate to your threat assessment or to your threat model. So if you're a nuclear power plant, okay, you need to plan for this. But if the question is whether people are trying to get your Instagram pictures, okay, do they really want to do this badly? On the opportunity side, what is the opportunity here? This is a low-power system with vast amounts of storage and wireless connectivity, and really, really low power, as in you could power it with a solar panel and put it up a tree. This is the ideal pirate box data exchange. If you don't know the term, pirate box is a device where people connect when they're in Wi-Fi range and put files or retrieve files anonymously. It's a way to exchange files. Or a spy.drop, if you want to go back to the Intel metaphor. Less ominously, you can make a solar-powered geocache. But seriously, now you can realistically put a server in your wallet. Or you could even make a server throwaway instead of an LED throwaway. Or you could put a Beowulf cluster in a shoebox, although I would strongly advise you don't. You could put it in the SD slot in your car radio if you have one of those, and then when you drive up to your driveway, the radio syncs the latest songs and podcasts automatically. And I'm sure that there are other things that I haven't thought about. There is one limitation. SD cards usually have SPI interfaces, and that would be awesome because SPI means Arduino. Sadly, this one does not. That won't work. But this is nonetheless a very interesting platform to experiment with. Cross-compiling is an option. You can also take the lazy way out and prototype with Perl. I solved the discovery problem for you. You have all the scripts. This is very low cost, same cost as the original Pi. So you have to decide if you want to trade RAM for very low power and small format, or the other way around. I think it's a fair question. It's a very nice hacking platform. Transcend has been very nice to the community. We broke this years ago, and they haven't complained. They haven't sued anybody. They haven't shut us out. They haven't done anything untoward. We get hardware to play with. They sell more hardware. Great for everyone. The mechanism we used is part of their SDK, but the SDK is not public, so we had to discover it the hard way. We need a better distro image instead of the crap that I've shown you. But that is relatively easy to do, and there are some out there, some initial efforts. For someone who has worked on as many Linux distributions as I have, the state of the images is not acceptable. We can do better. But there are adequate things to at least experiment. So if you come up with new ideas or on how to use it, please send them to me. Here's my contact info. If you can, find me on Twitter or send me email. Remember that speakers are Pavlovian devices. So if you like the talk, please let us know, rate the talk, send comments, submit feedback, all of that. If you do something with it, let us know so we can include it in the survey paper. Slides will be available, and I'm here for questions if you have any.
Awesome. Here's a small token of our appreciation. Thank you very much for a good talk. Give them a big round of applause.
Thank you. Oh, thank you.